This lecture is on the effects of functional groups. The underlying principle of functional groups is that function follows form. A functional group is an atom or a group of atoms with characteristic chemical and physical properties. So for instance, if we take three functional groups as an example, an ether group, an alcohol or a hydroxyl group, and a carboxylic acid, we can look at how they differ in spite of the fact that all three of these compounds have carbons, oxygens, and hydrogens. Let's start by comparing the ether with the alcohol or hydroxyl functional group. An ether functional group is an oxygen that's linked to two carbons, and an alcohol or hydroxyl group is an oxygen that is linked to one carbon and one hydrogen. In this particular case, we have taken constitutional isomers. That is, these two specific molecules have the same molecular formula but differ in bonding. And you would think that constitutional isomers would have similar properties. However, if we just take a boiling point as an example, this ether has a boiling point of 36 degrees, while its corresponding isomeric alcohol has a boiling point of 118 degrees. And this is all because of the functional group that is present in the molecule. The presence of this OH implies that this compound can undergo hydrogen bonding, and that's what gives it a higher boiling point. Now let's compare an alcohol to a carboxylic acid. You can see that both the alcohol and the carboxylic acid have this OH group. However, a carboxylic acid also has a carbon double bonded to oxygen. So the carboxylic acid functional group consists of a carbon that's double bonded to an oxygen, single bonded to an OH, and bonded to another carbon. If we look at these two molecules, even though they have the same number of carbons, they have very different pKa's. This is just an example of chemical reactivity and how functional groups confer different chemical properties onto these molecules. Despite the fact that both these molecules have an OH bond, these two protons on that oxygen have very different acidities. This proton is much more acidic and has a much lower pKa than the alcohol proton. And so if you take one equivalent of base and add it to a mixture of these two compounds, this carboxylic acid proton will react first. That explains why we're interested in learning about functional groups. Functional groups are groups of atoms with characteristic chemical and physical properties, and the significance of it is that since this behavior is unique to the functional group and is therefore similar regardless of what molecule it is part of, understanding their behavior makes it easier for us to predict the outcome of reactions. Functional groups are also usually considered the reactive part of the molecule, and that can be due to the presence of a heteroatom such as nitrogen, oxygen, phosphorus, sulfur, any of the halogens, all of which possess lone pairs. It can be due to the presence of pi bonds, as in alkenes or alkynes. Remember that pi bonds are weak or easily broken. It can also be due to the presence of positive charges, such as carbocations. Now we're going to look at the effect of functional groups. Functional groups can affect physical properties like intermolecular forces, and it also affects chemical reactivity. We will study chemical reactivity of different functional groups in detail. For now, we're going to look at some of the physical properties and how they are affected by functional groups. Ionic compounds have extremely strong electrostatic interactions, and so they have very strong intermolecular forces. This leads to a very high boiling point and also a high melting point. The melting point is also increased due to better packing in the crystal lattice. As far as solubility goes, ionic compounds are soluble in water. Remember the principle that like dissolves like? Ionic compounds are polar, remember their charge, and so they're soluble in polar solvents like water. In organic chemistry, we're focusing on covalent compounds, and so our interest lies in these three intermolecular forces: van der Waals forces, also known as London forces or London dispersion forces, dipole-dipole interaction, and hydrogen bonding. Van der Waals forces are very weak, They're caused by temporary dipoles in the molecule, and they're always present in covalent compounds. They depend on surface area of compounds, and they depend on the polarizability of each compound. The dependence of surface area explains why propane is a gas and hexane is a liquid. If we think about the surface area of propane, which has just 3 carbons, and hexane, which has 6 carbons, hexane has a greater surface area. And so there's more interaction, stronger van der Waals forces, and that's what leads the boiling point of hexanes to be higher. Dipole-dipole interaction is slightly stronger than van der Waals forces, and it's caused by permanent dipoles in adjacent molecules. When we talk about permanent dipoles, we mean that the molecule has to have a dipole moment. For instance, in acetone, we know that the electrons are being pulled towards this oxygen, and the molecule always has a dipole moment where the oxygen has a partial negative charge, and this carbon in the carbon-oxygen double bond has a partial positive charge. In solution, acetone molecules will line up according to their charges, and that provides the basis for the dipole-dipole interaction. And now we come to hydrogen bonding. It's the strongest intermolecular force in covalent molecules. Remember that it's still weaker than a covalent bond, though. Now we're only talking about intermolecular forces, and hydrogen bonds are the strongest of these 3. The classic example of hydrogen bonds is water, and you can see that in water, the electrostatic interaction between a hydrogen that's bonded to an electronegative atom and another electronegative atom's lone pair is what provides the hydrogen bond. In general, when we talk about the electronegative atoms that can undergo hydrogen bonding, we're talking about fluorine, oxygen, and nitrogen. All these intermolecular forces affect physical properties, for example, the boiling point, the melting point, and solubility. For boiling point, we look at the strength of the intermolecular forces and the surface area and polarizability of the molecule, and these two go back to the van der Waals forces. For melting point, we look at the intermolecular forces as well as the symmetry of the molecule to assess how well it can pack in a crystal lattice. And for solubility, remember the principle that like dissolves like. So nonpolar compounds will be soluble in nonpolar solvents, and polar compounds will be soluble in polar solvents.